Okay, guys, so this was kind of an improvised meeting. Me and Vartan met like a week ago, and he proposed that I should come and talk about the problems that I face while designing software. And the kind of software that I designed is kind of a little bit unusual for most developers, because like first you need to design software, then you test it, and generally if it works, no one touches it, and they just keep it that way until it breaks again, and then they have to rewrite it again over and over. For us, there's like one more step at the end, benchmarking, so that we not only design software that works, but we try to design the software that works best. So the title of this talk is a little bit misleading. So it's Peta-Scale software design in 2021, or how not to go bankrupt on AWS charges. But I don't really do too much stuff on AWS. AWS is kind of very expensive, and it's not the best solution if you want to scale to the limits where I want to go. So before we go further, I should probably introduce myself. Oh, didn't expect that one. So my name is Ashot. I've been programming, I guess, for 10, 15 years, depends on how you count. I'm 25 right now. I've been building software businesses for about 10, 15 years. I was doing web development when I was a kid in elementary school and mid-school. I was mobile developer in high school years, and then I was doing scientific computing during my astrophysics degree, and then I dropped it because I had a lot of research being done in the realm of AI and high-performance computing. So I started merging every single part of the code that I wrote in the past few years into the system or the company that I call unum these days. And unum is the Latin word for unity, because I tried to unify all different approaches that I've been working on for decades into one single thing. And in the past few years, I've given a bunch of different talks related to AI, mathematics, programming. Some of them were recorded, and like if you're interested afterwards to learn about how you program GPUs, or how do you do like assembly programming, how do you benchmark it, how do you design advanced neural networks, you can just search it on YouTube. Some of them will pop up. So the first question is like, why do I do this? The idealistic answer is that we want to make the world a better place. And AI these days is like one of the most advanced technologies, not just from the implementation perspective, but also from the benefits it provides. So those are breast cancer scans. And these days, if you take a bunch of oncologists, high-end oncologists with 20 years of experience, and you put them next to a neural network will be more successful in identifying the cancer cells on the scans than a bunch of, let's say, Israeli doctors. This is a little bit more fun if you don't want to be like too serious. This is a neural network used for robotics. So imagine taking a neural network and teaching it how to take like a model, a 3D model of a system, a robotic system, and manipulate it so that it fights gravity. So like the first few iterations of the neural network, they are kind of stupid, let's say, like not really a smart neural network. So the first 10 iterations die and fall. They don't know how to control their own muscles. But then 1,000 iterations of learning further, you have a neural network that's relatively successful in manipulating any set of muscles you can design. And then if you want to do something closer to what I do, which is natural language processing and knowledge extraction, you can take a natural language model such as GPT-2 or GPT-3 and browse a demo like this. So you can just type a query like Code Republic is the new programming school, and let's see what it outputs, like founded in 2011 by former or something like this. And there is not really a piece of text on the internet that you can find that says that Code Republic is something. So all you see on the screen was kind of imagined by the neural network. It didn't know anything about Code Republic, but from the context, it tries to infer what comes afterwards. And this is extremely non-trivial. So the neural network that it uses under the hood, I guess, is GPT-3. And GPT-3 is a neural network of a transformer design, if this tells anything to you, with 175 billion parameters. So if you know anything about how neural networks work, is just a set of matrices multiplied one on the other, and a bunch of nonlinearity stuck in between them. So you have like a sigmoid function or some other nonlinearity between your matrix multiplications. Guys, you should probably sit somewhere there because otherwise you will not see the screen. So GPT-3, the neural network that was used to generate those sentences and this text, it actually has 175 billion weights. So when you train the neural network, it has those matrices which kind of encode its internal representation of knowledge, what it learns during the training. And after you train it, every single one of the 175 billion floating point weights has to have an optimal value. So it's like a task that is impossible to solve like with absolute accuracy. You cannot find the ideal weight because like for every float 32 value, you have 4 billion potential values because it's 2 to the power 32. And you have 175 billion of those. So the total number of combinations that you can have is 4 billion to the power 175 billion, which is not really computable. So to do this, we use stochastic gradient descent, a bunch of other different interesting algorithms to kind of find the, maybe not the best, but relatively good working solution. And the family of natural language processing problems is really big. So one of the other things that you can do is that you can actually write a query like this. Yerevan mask is a beautiful ancient mask in the middle of the mask. And then for every single mask token, this neural network will kind of try to predict the optimal word that fits the context. And from one year to another, every model gets better and better, but not only because the model itself becomes better, it just scales and becomes bigger. It has more weights and it requires more compute to actually be optimized to converge to a specific good model of knowledge. So how big of a problem is this? There's this company called Lambda Labs. It's a California-based OEM manufacturer. So essentially, they build up servers, mostly for AI. And they kind of try to estimate how expensive it is to train a neural network like this. So a GPT-3 model with 175 billion parameters probably costs you about $4.6 million to train. So if you just take servers that you already have, or like you rent those servers from AWS, and spend enough time for this model to actually converge to adequate knowledge state, it takes you $4.6 million of value to actually rent those servers until you get to the final point. So not only the amount of money is a big problem, it's also a problem of time. So if you have a neural network that takes so many iterations of training to converge to a good model, you probably need to scale it to more than one server or more than one device within a server. Because if you just take one single advanced GPU, such as RTX 8000, which is like a relatively expensive GPU, probably like $10,000 or so, it will take you 675 years to train it. Because you can parallelize your problem into multiple different smaller chunks that can be distributed onto a cluster, you can converge to a final point much sooner. Another example that I don't have here is chess, and Armenians love chess, so probably I should have added that example as well. There's a company called DeepMind in London, and what they do, they actually spend months and years designing models that can play games. Maybe not as noble of a cause as fighting cancer, but still relatively interesting. And one of their recent models called AlphaGo Zero can actually train itself to play chess much better than any human could do in human history in just a matter of 4 hours. So you take a neural network that only knows the rules of chess, it kind of replicates itself and plays against itself, so it never looks at any games played by humans, and in 4 hours it reaches ELO rating of 3,400. The highest rated human chess player is 2,800, and 100 points difference in ELO ratings essentially means that you are not really going to win this person even once in 100 games. Like, this is close to this matter of difference. So 4 hours sounds like extremely short period of time, but the reality is if you take not a cluster, but if you just take and convert the number of games that it plays into the number of into the amount of time that it takes a human to play a game, it actually amounts to centuries and millennia of playing chess. So if you were just born and from the day zero of your life, you only play chess 24/7 with the average length of a game, it takes you maybe like 5,000 years to probably play as many games as it takes neural networks to play 4 games. Okay, enough with AI. Let's talk about parallelism, something closer to programming than AI research. So now the next couple of slides will be like very elementary level, but we have very different levels of developers here, so I guess it makes sense. There's this trend which is called Moore's Law, and by now I guess everyone knows what it is. It's essentially a prediction that the compute capacity will double within every next 2 years, or every 18 months, or every 12 months. Kind of the actual number of months it takes to double doesn't really matter that much. It's more of a trend thing. So if you look into 1970s, the number of transistors that you had on the chip was about 1,000. But these days, in 2020, we have tens of billions of transistors on every single chip. And without this, the AI revolution wouldn't be possible. But the trend itself is much more complicated inside. So if you take this trend until probably year 2000, you will see that most of the increase was actually in single core performance. So when I was born, the CPU frequency could have been, let's say, 400 megahertz. So 500 or 400 operations per second. And then by the time we actually reached the plateau in the single core frequency, the plateau was at about 1.5, maybe 2 gigahertz. And this is what you get in laptops or computers today. So if you take even this laptop that I'm using right here, it's not really faster than the laptops 10 years ago in single core performance, not that much faster. It still does 2 billion operations per second. The difference is that it's not really doing one operation after another. It's mostly trying to do multiple operations at the same time. And this is actually what we call parallelism. And there are many, many flavors of parallelism. The most known ones today, depending on which programming language you're coming from or which industry you're coming from, is multiprocessing and multithreading. And this is relatively easy thing to actually acknowledge. Well, you take a CPU, on the box it says how many cores it has and how many threads it has. And you actually just take your model, you take your program, and instead of running one instance of a program, you can launch maybe 8 instances of a program on 8-core CPU. And every instance of the program will actually run as a separate program by itself. This is what's called multiprocessing. So every program, every instance is completely separate from the other. They have separate address spaces, and it's not trivial how you send data from one instance of the program to another. There's a slightly different mechanism that actually utilizes parallelism on the same level. When you have many cores, you can still launch one single application, and it internally creates a thread pool, which is not, let's say, one single thread, but maybe 8 threads, and it balances different operations within your program between those threads. And this is the model of parallelism that is more common in maybe lower level languages. In languages with coroutines, it's also common. So Go kind of implicitly internally creates this thread pool, and you create coroutines, which are like small tasks that you submit into those threads. It internally finishes them, provides you callbacks, or provides you a continuation handle, and you just wait till one task finishes and you jump to the next one. So to give you a perspective of how many cores or threads you can have, a laptop like this comes with 8 threads, or this one specifically comes with 8 cores and 16 threads. A high-end server CPU comes with maybe 128 threads. But as you can have, let's say, 2 CPUs on the same motherboard within the server, you can have 256 threads. So if you are able to do this kind of parallelism, you can transform your single-threaded operation or application into a 256-threaded application. And depending on what kind of application you have and what kind of communication patterns you exploit within your application, you can get a 256 performance improvement for your same application. So the kind of problem that's easiest to parallelize in this way, you take a big array of 10 million elements, And you take the second array of 10 million elements and you do pairwise addition. So you add the first element of every array to the first element of the second array, and you output the sum into the third array. And this is what's called data parallel applications. But beyond those two levels of parallelism, there's a lot more interesting stuff that happens in the computer that far less developers know or use. One of my favorite solutions is what's called SIMD, single instruction multiple data, or multi-data approach. So essentially, you have your computer, it has 256 threads, and maybe it can manipulate more than one piece of data per thread. So essentially, if you take a computer, if you take the CPU design, it will have a separate cache registry for instructions, a separate cache registry for the data pieces that arrive, and maybe if each instruction can be applied to more than one data piece. So essentially, every single instruction simultaneously operates not on 32 bits of data, which are two 32-bit integers, but maybe it takes a chunk of integers, which are 512 bits of length. It divides it into 16 parts, and it operates those vectorized instructions. So if you take x86 assembly from today, or if you take ARM assembly, those assembly families, they actually have subfamilies of instructions that are vectorized and can operate on much bigger chunks of data. But now we kind of went from multiple threads into multiple operations per thread, one level down. Can we go one level up? The answer is yes, sure. So besides CPUs, modern servers come with all kinds of other accelerators that are installed in the same server. And when you do AI training per se, you actually take a server which generally comes with 2 CPUs and maybe 8 GPUs. And those 8 GPUs have different hardware architecture that are optimized for different families of operations. And depending on what kind of operation you do, it makes sense to actually distribute it to a GPU, to FPGA, or what is called ASICs. So GPUs are graphics processing units. They were originally used for graphics, obviously. But then maybe like 10 years ago, people like me realized that you can use them for something different. And about 10 years ago, I was doing physics simulations on GPUs, and then I started doing AI on GPUs. FPGAs is what's called field programmable gated arrays. And then you kind of design the hardware for this FPGA as part of your program. But once you are big enough and you have huge volumes, maybe you have hundreds of millions of dollars of assets and you want to spend it on compute, you can actually crystallize your FPGA design into an ASIC, which is application-specific integrated circuit. And a good example of those is mining devices for cryptocurrencies. Can we go even higher? The answer is yes. This is what's called multi-node parallelism, and it comes in 2 flavors, I should say. The 2 biggest groups of multi-node operations are probably supercomputers and data centers. So a difference is that a supercomputer is something like you find in a university. So you want to do big weather simulations. You want to do big physics simulations or something like that. You want to analyze how the genome works. You want to do protein folding. For this, you combine servers into a very high bandwidth network. And this can be maybe hundreds of racks and thousands of servers connected with extremely high performance networking. And stream processing or data centers are kind of different. You have a lot more nodes, so maybe thousands or tens of thousands of racks of servers and maybe millions of servers, but they're not that densely connected with each other. So for data centers, the workload can be running something like Facebook's backend or Google's backend. So just to sum up, the difference is that multi-node is separate machines. Multi-device is when you have different devices within the same server, and each of them comes with their own memory pool, their own maybe operating system or model of execution. Multiprocessing and multi-threading are kind of the same thing, but with different flavors. So you have a program that's parallelized within the same CPU cores, and then within the CPU core, you can do multi-data. And the way you program those things is mostly in C or C++. So C is pretty well known to be the language that's closest to hardware out of the hardware invariant languages. So assembly in the bottom line over here is not one language, it's a family of languages, and every single CPU architecture comes with their own separate assembly. But if you want to do something relatively generic, you are basically stuck with C and C++. Some other languages may have wrappers for some operations. So in Java or in C# or in Rust, you can find wrappers for SIMD instructions. But the point is, those wrappers are not really native interfaces, and they're very much constrained to what was implemented on, let's say, compiler level, language level, library level, whatever. C and C++ are what by far gives you the biggest access to hardware and utilizing every single piece of hardware that's provided. So what kind of performance improvements you can get when you're doing something like this? So you have an app that runs in a single-threaded environment. It's a 1x performance. If you do something like multiprocessing, you can make your program run 50 times faster on the same CPU. If you do something like multi-threading, maybe you can do it 100 times faster on a computer with 100 threads. If you have, let's say, a GPU that is connected to your CPU, sometimes you can get to 100x improvement. And a good example of this is, again, AI in the matrix multiplication operations that arise there. So an AMD EPYC 7742 is a CPU with 64 threads, 64 cores, 128 threads, I guess 256 megabytes of cache, and it costs probably about $10,000. That's the order of magnitude. And then if you take an NVIDIA A100 GPU, it also costs about $10,000. But on some operations, the CPU will be 10 times faster than the GPU. But as soon as you can make your operation GPU-centric, you can make it 100 times faster. So essentially, you have two devices that cost the same, but one is 100 times more cost-efficient than the other. And it's a huge difference, because when you're building a data center to train neural networks like this or to run big businesses, your cost of constructing a data center can be tens of billions of dollars. Or maybe just billions of dollars. And the difference between spending $1 billion and $100 billion is the difference between a $1 trillion company and a $1 billion company. A $1 billion company would never afford to do the same things if not for the more optimized hardware. So one of the interesting aspects is that multiprocessing and multi-threading kind of utilize more or less the same hardware capabilities, but one is only 50 times faster and the other one is 100 times faster. Do you guys have any guesses why this is the case? There is no competition here. We're just like having a friendly gathering, so all the guesses that you'll have are valid. Why can be multiprocessing two times slower than multi-threading? Anyone?
Multi-threading-ի ժամանակ նույն address space-ն է, դրանով հետևաբար ավելի արագ է, քան տարբեր process-ներ, տարբեր address space-ներով։
Բայց ինչն է դա նշանակում, ինչ լիմիտ է դա մեզ, so like what's the limit from actually doing separate address spaces? You are kind of talking like heading in the right direction. Yeah?
CPU-ի մեջ context-ի switch չի լինում։
Չէ, կլինի, նույնիսկ multi-threading-ի ժամանակ, վատ միտք չի, բայց սխալ է, էլ ինչ-որ մտքեր ունեք։
Swap-ի աշխատանքին բարդ process-ներ swap memory հետ աշխատանքն հիմնական։
So the right answer is that, let's say you have an application and it operates on a big array and you have two cores and you want to split the problem into two smaller parts. One core takes the one half and the second core takes the other half. If they're not operating in the same address space, it means that first they need to synchronize who takes what. There is no thread or shared registry where you write who does what. And then besides that, for you to send the data between the first and the second thread, you cannot just provide a pointer to this data, because as soon as the other process will try to access the pointer that was provided for the second half of the data, it will get an error, a segmentation fault probably from the operating system. So an operating system is actually responsible for seeing who's trying to access what kind of data, and it will ban you if you're trying to access the data that wasn't allowed to you. So you need to physically copy the data from one process to another. And for this thing to happen, you actually need to open up a socket, so essentially a networking process. And you write the data into this socket. And then the other thread, another process, should read from this socket, deserialize the data, and only then start operating on the data. So it requires physical copies and a lot of networking. And for networking to happen, the data physically leaves the RAM, it physically leaves the CPU, it goes into the networking card, potentially, or maybe it doesn't leave. But anyways, like there are a lot more pieces involved, so you get a much lower performance. Okay, so actually, like every single topic, every single layer of parallelism in this thing is not even a topic for a 2-hour talk. It's maybe a topic for a couple of years of research. And I've given talks on some other layers of infrastructure, so I guess now it's the time to talk about networking. And it's a relatively good example of the design problems that arise if you're trying to write software on the scale that I generally work with. So if you look at the TCP/IP protocol stack, you will probably see something like this. And if any of you have like formal training in computer science or programming, or just studying it right now, you've probably seen this table in one shape or another. So what happens when a technology stack becomes relatively mature? We design layers of abstractions to actually separate the research that happens in one layer and another. And this standardization, counterintuitively, kind of provides us more flexibility to research within the layer, but a little bit less flexibility between the layers. So generally, people separate the 7 layers of the protocol stack: the application, the presentation, the session, transport, network, data, and physical. And on every single part of this layer, you have like a dozen of different choices which you can combine and mix together to get a full stack. So this is how everyone does networking these days. So whenever you say you have a client-server application, maybe a mobile app, you have a device that sits in the hands of users, which is maybe like an iPhone. And an iPhone is not really very powerful because it has like a small battery. You don't want to spend all the energy doing some form of computation. So instead of doing all the complicated computations on the device, you can actually rent a big server somewhere in the cloud. And whenever a user wants to do something complicated, you just send a request from here into a server, and the server does all the heavy lifting, and it sends you the result. This is how it generally works. And for this, you utilize this TCP/IP stack. And what they don't tell you at schools, probably, is that there's a lot of redundancy in what happens over here. So essentially, like you want to utilize something like HTTP, Hypertext Transfer Protocol, to actually send maybe web pages through the internet. But today, they don't really use pure HTTP. They use HTTPS. And HTTPS is different because S stands for security. So you want to be more secure while sending the data through the internet. And before you can send the data, you actually do what's called a handshake. So a client connects to a server, and before they start sending any relevant information to each other, there is a process of handshake. So essentially, a client and server connects to each other, they create a bond, and they store some different keys and secrets which help them compress and encode the data before they send it to each other. And then once you go one layer down, maybe like into the transport protocol such as TCP or something different, you will see that on this layer there's also like something like an encryption, or there is like a way to compress the data. There is a way to actually add a header before the data comes. And every single layer of this infrastructure actually appends some metadata to your packet, the packet that you're sending from one device to another. So before we start looking into something like a networking stack, I guess there is like something easier that we can talk about. Let's say you have something as simple as associative container. So essentially you want to store something like a dictionary. You have a key, you have a value, and you want to have a container which stores keys and values with a relatively high access speed. So whenever you provided a key, it returns you a value that was stored within the same key. There are tens of designs for binary trees, such as AVL tree, red black tree, Tango tree, like you can read the rest. And then you can have something that's different from a binary tree. You can have a container which splits to more than 2 nodes on every single node of this tree. And this is what generally called a tree or a trie, depending on the design. And you can also have hash maps, and there are hundreds of designs of different hash maps. So for your simplicity, library designers such as the C++ Standards Committee, which designs STL, Standard Templates Library, have selected the 2 tree designs or 2 container designs that they provide to you in the form of containers. So you've probably seen what's std map. It's also an associative container which internally is implemented as a red-black tree. And if you use std unordered map is actually one of the designs of a hash map. So as soon as you get from like common software design to a level of high-performance computing, using standardized containers may not be the best choice because they're created for the average case or for low performance applications. But the point is there is no such thing as average case. Like if you take just a hospital and you measure like the average body temperature of every person, you get some value and then maybe like 4 points after the comma, 4 digits after the comma. But the thing is that no one in the hospital may have this specific temperature. They can have something that varies with a specific range of this temperature. So even when you work with std map or std unordered map, as soon as you need high performance, you're immediately facing some bottlenecks. So if you go to this website, tessel.github.io, there is a perfect blog post about different hash maps and their implementations. And even on the very basic operation of adding integers into your hash map, you see huge variance in the performance. And you would think that the C++ Standard Committee should have done a great work in standardizing some good container. So probably if the strongest developers on the planet have found that this is the best solution, it will be the best solution, and it may be the best, but it's best for some average case. For every specific case, for every specific environment, your results may vary significantly. So here he takes Google Dense Hash Map, which can be found on GitHub, QHash, which is a hash map implementation from Qt library, and also 3 hash map implementations from the TSL library. And he shows that in some cases, creating a container with 3 million elements can work easily 4 times faster when you use some other library other than std unordered map. And this is like one of the most basic benchmark examples. But even here, like there's a dozen questions that come to mind. So the first one is threads. Is he doing this benchmarks in a single thread environment or multi-threaded? What if you have a container and more than one thread is trying to write into this container or read from this container? And for people who are less familiar with multi-threading or just parallelism in programming, imagine that you have some task in your office or maybe in school. A teacher asks you to write an essay on a piece of paper. What if you have 4 students and they try to write the same essay simultaneously on the same piece of paper? It will be extremely hard because some of them will be actually writing the same sentences over and over, one on top of the other. They will be kind of limiting each other's performance. You'll have data races, you will have collisions, you will have all kinds of problems that arise in multi-threading. Another problem is keys distribution, but this one is a little bit more complicated, so I'll just skip it for now. Another one is value sizes. What if you are just putting keys and values together, and the value is 100 times bigger than the key? Depending on the data layout inside your memory, you can have a hugely different performance on how you access and write the data. And there are also like a dozen more questions that come to mind, but I guess we can just come back to those if you're interested afterwards. So if you are stuck with this kind of performance-oriented approach, Obviously, you cannot optimize every single line of your program, but you can at least use some kind of heuristic or some kind of basic knowledge to understand which parts require optimization more. And this is quiz time again. So guys, this is a table, and we need to fill it together. Like if I ask you, how fast can a CPU perform integer addition? If I give it two integers, one int64, another one int64, and ask it to accumulate those two integers into the third value, how many CPU cycles or seconds will it take? How do you think? Who has a guess? Guys, don't be scared. Like, we are learning all together. Yes? So integer addition-ը մի cycle է։ Մտածում ենք, որ data-ն արդեն այնտեղ է։ Հաջորդ տողը առաջին տողն է, ALU, Arithmetic Logical Unit։ Երկրորդ տողը load from SRAM, սա ինչ է նշանակում։ Ունենք CPU, ունենք RAM-ից բացի CPU cache-ը։ Cache-ը դա SRAM ստրուկտուրա իր մեջ ունի։ Ինչքան ժամանակ կտևի, մինչև մի բայտը կամ 8 բայտը կարդանք SRAM-ից դնենք ALU հաշվելու համար։ Խոսքի հաշվելը հասկացանք, որ մի instruction-ա տևում։ Ինչքան ժամանակ կտևի, կոպի անենք այդ մի value-ն հաշվելու համար։ Ով կարող փորձի։ Հա, SRAM-ից, դա ոնց որ արագ memory է, CPU cache-ն է։ SRAM-ից կոպի անենք ALU-ի մեջ, որ հետո գումարենք երկու թիվը։ Ինչքան ժամանակ կտևի։ Քանի CPU cycle։
Եթե single data rate-ը,
երկու cycle։
Եթե single data rate-ը, մի cycle։
Մի cycle, երկու cycle, ով կտա ավելին։
Ուղղակի data-ի չափն է, չէ՞ կարևոր։
Նախ մտածենք, որ 32 բիտ է, 4 բայտ է, այդքան էլ ճիշտ ասած մեծ չի տարբերություն ունի։
Մենակ արթում ենք RAM-ից, թե գնահատում։
RAM չէ, SRAM։ SRAM-ը տարբեր է, RAM-ին հələ կհասնենք։ RAM-ը դա DRAM-ը կոչվում, դա նախավերջին տողն է։ Ահա, մի cycle, երկու cycle, ով կտա ավելին։ 3 ավելի շատ ով ավելի շատ կտա 3 արդեն ունենք 3 cycle լավ թող լինի 3 cycle ամեն տողով չանցնենք եկեք համատենք DRAM-ի հետ DRAM-ը դա RAM-ն է խոսքի որ առնում եք կոմպը գրած է որ 15 GB RAM կա մեջը ինչքան ժամանակ կտևի այդ նույն 4 բայտը ոչ թե SRAM-ից կարդանք, որ համարյա CPU-ի մեջ է արդեն, այլ DRAM-ից կարդանք, որ ոնց որ առանձին չիպ է motherboard-ի վրա։ Երևի ավելի շատ, որովհետև ավելի հեռու է։ Արդեն ունենք մի cycle 2, 3, չգիտեմ, 10 կարող է, ով ինչքան է մտածում։ 10։ Բավականին շատ է, կարող է դրանից էլ ավելի ստանանք։ 10 դե լավ տենանք ճիշտն ասած 10 չի նայեք ռեջիստրները դա ոնց որ արդեն CPU-ի մեջ է CPU-ից որ վերցնում ենք երկու թիվ ու գումարում ենք իրար հետ դա մի CPU cycle է դա բավականին արագ է եթե դուք 3 GHz-անոց CPU ունեք անում է 3 միլիարդ operation վայրկյան դա նշանակում է, որ մի նանոսեկնդի երրորդ մասն է օգտագործելու integer addition-ի համար, 0.3 nanosecond։ Եթե ուզում եք level 1, level 2 կամ level 3 cache-ից հավաքեք, ավելի երկար ժամանակ կտևի այդ դատան, խոսքի այդ դատան հանելը։ Level 1 cache-ից կարող է մի 2-3 clock cycle տևի, level 3 cache-ից էտել է ոնց որ SRAM կտևի մի 10 CPU cycle կամ 20 արդեն 3 չէր 10 էր բայց որ ներքև ենք իջնում DRAM մեզի կտևի մոտավորապես 100-ից մինչև 300 CPU cycle Խոսքի որ մենք data-ն վերցնում ենք RAM-ից, մեզի 300 անգամ ավելի էժան է computation անելը, քան թե ուրիշ data վերցնելը։ Դրա պատճառով մենք ուզում ենք այդ data load-ները ինչքան հնարավոր է քիչ անենք։ Խոսքի մի անգամ load ենք անում ու հետո 300 անգամ իր վրա operation ենք անում ու դրա եթե տենց անենք, բավականին balanced կլինի։ Եկեք ժամանակի կեսը կծախսենք data հավաքելով, ժամանակի կեսը կծախսենք հաշիվներ անելով։ Եթե ուզում եք SSD-ից ինչ-որ բան կարդաք, էդի արդեն միլիոն cycle կարա տևի, 10 միլիոն cycle։ Ու նույնը networking-ի համար է ճիշտ։ Խոսքի եթե ուզում եք data packet, նույնիսկ data center-ի մեջ ուղարկեք կողքի server, էդի կարա 10 միլիոն cycle տևի, նույնիսկ 100 միլիոն cycle, նայած ինչ տիպի connection ունեք։ Փաստորեն միլիոն անգամ ավելի էժան է computation անելը, քան թե ուղղակի մի bit ուղարկելը։ Ու տարբերությունը այնքան մեծ է, որ ճիշտ որ ասեմ, այդքան էլ մարդիկ չեն մտածում, մի bit-ա, 10 bit-ա, 100 bit-ա։ Ուղղակի եթե պետք է անես, դա արդեն վատ է։ Ու մենակ ժամանակը հարցը չի, մեկ էլ էներգիան է հարցը։ Խոսքի LU-ի վրա, որ երկու հատ թիվ գումարես, դա մի պիկաջոուլ կտևի, մի պիկաջոուլ էներգիա կծախսես։ Բայց նույնիսկ DRAM-ից հանելով, data հանելու ժամանակ, մի նանոջոուլ կծախսես։ Խոսքի պիկոից հասանք նանը, 1000 անգամ ավելի թանկ է։ Ժամանակի տեսակից 100-ից 300 անգամ ավելի դանդաղ է, ու էներգիայի տեսակետից 1000 անգամ ավելի թանկ է էլի։ Ուրեմն ուզում ենք այսի ինչքան հնարավոր է քիչ անենք, բայց սաղից քիչ ուզում ենք networking access անենք։ Ու եթե մենք ինչ-որ app ունենք, որը որ ոչ թե մի սերվերի վրա է աշխատում, այլ մի քանի սերվերի վրա է աշխատում, կամ էլ ունենք client եւ server, ուզում ենք որ իրանք այնքան հնարավոր է քիչ իրար հետ խոսանք, որովհետեւ այդ խոսալը բավականին թանկ օպերացիա է։ Ու եկեք նորից վերադառնանք այս նկարին։ Սրա վրա տենում ենք, որ մի 1000 հատ տար կա, չգիտեմ, ամեն մեկ ինչ-որ բան նշանակում է, ու եթե սկսում ես իրենց դոկումենտացիան կարդալ, ամեն մի այս պրոտոկոլի implementation-ը մի 100 page է։ Implementation-ն էլ մի, չգիտեմ, 100,000 տող է C++ կոդի։ Բավականին բարդ ստեկ է, ու դու չես ուզում նույնիսկ տենց hashed data exchange-ի համար այս լրիվ TCP/IP ստեկը օգտագործես։ Չես ուզում ես լրիվ abstraction-ները քո պրոյեկտ տանես, եթե ուղղակի ուզում ես կողքի սերվերից կողքի սերվեր ինչ-որ բան ուղարկես։ Ու աստե ես էլի վերադառնում եմ անգլերեն։ So all of those protocols were actually designed for very specific use cases, and they may not be bad per se. But if you are just looking from raw performance perspective, if you just need to send the data from one part to another, there are so many inefficiencies in every single part of this. Oh, that's bad. Who has a charger for a laptop, for MacBook? I'm running low on energy. I hope he's coming back with a charger and not just exhausted from the lecture. Okay, let's go forward. And let's see how modern data center engineers tackle the same problems. So on the right is the performance stack as we know it today. Essentially, you have the application, transport, network, and everything else. And in between, the orange part is actually what the kernel code is. The kernel is like the operating system. And between your application on one server and your application on the other server, there is like two operating systems that sit in between and two hardware stacks that sit in between. So essentially your signal from your application goes into your server's operating system, then your server's hardware, through the network into the other server's hardware, into the other server's operating system, and then into the other server's application. And the engineers in the past decades have been trying to actually optimize this stack, remove all kinds of bottlenecks and inefficiencies from it. And today we actually came to the point when we actually eliminate the operating system whatsoever, and we talk to the hardware from the application directly. And this is again what you can do almost exclusively in C and C++. So today's protocols are built not on TCP but more like on the UDP if they use the IP stack. They use InfiniBand, and some other fancy tokens or like keywords that may not tell you much today, but if you go deep into this industry, you find out some cool technologies such as RDMA, remote direct memory access. So what this means is essentially you have a huge address space into which your different applications running on different servers can write, and this is like a transparent address space for all the devices. And not only your CPUs can write and read from the same memory buffers from the shared memory of your entire data center, but also each GPU can access the memory of every single other GPU. And not only you connect thousands of CPUs together, you can connect tens of thousands of GPUs together into a huge AI cluster. Today, the networking stack looks something like this. If you're designing a high-performance software for your data center, so again, you have even more protocols that we had before, but all of them are much lower level. So essentially, you can control how not only the data is sent between the servers, you can actually programmatically control how the data is exchanged between the devices within the same server. So you can send the data from one GPU to another, you can share their memory pools, and for every single part of this infrastructure, there's a separate library. But essentially, like whenever you're designing something like this, you should always keep in mind what's the final goal. Like, why are we doing all of this? Because there is some hardware part, and we need to be optimal, not just like in the vacuum, but for a specific set of hardware. So if you take a server that's common in AI workloads today, this one is called NVIDIA DGX A100, a single server like this costs $200,000. So this is like a Bentley, but in a data center. And if you look deeper into this picture, it's actually pretty well visualized. So you have 8 GPUs over here, a couple of CPUs over here, 10 networking cards, and every part of this huge infrastructure has to be perfectly orchestrated. The problem is every device in this system has a different purpose. Some of them are used for, let's say, matrix multiplications, mostly in AI. The other ones control how the data will be orchestrated, organized. The other ones are responsible for sending the data. Another one, such as SSDs, are the persistent storage. When the energy goes off, when you turn off the computer, you have to store somewhere your data. Because every single device has its own different purpose, it's actually normal that all of them require different protocols. It's not really like just a wish, it's a necessity because the hardware is so different. So the worst case scenario is actually you looking into all of those details that I actually showed, coming back home, spending 2 years optimizing this entire software stack, and then realizing you don't need all of it. So you write a ton of software, you install it on your system, you benchmark it, and the execution time is the same as 2 years ago. So nothing changed. So for you to understand where you need the optimizations and how to do this, like the education and practice and experience is absolutely crucial. It's impossible just to like watch a couple of lectures or a couple of talks and then be certain that you know how to program this stuff. So to me personally, a definition of a senior developer is a person who has a lot of experience, so he kind of knows which approaches work out of the ones he tried and which approaches don't work. But then there's like a difference between stronger and weaker senior developers. The strong one is the one whose knowledge is relevant. So all of those protocols that I've showed, it took decades to engineer all of those. We started in 1980s, 1990s, and in the past 30, 40 years, we've been just designing protocols. If your knowledge is from 1990 or 2000, it's not relevant. Like, the protocols that they used before are not really used anymore. So you have to be always on the edge. You have to always innovate, always research what's possible, but... merci. So if you take all those protocols, even the newest ones, and try to see how they combine, mix, and match together, you end up with combinatorial explosion again, because like the number of ways how to sample different parts of a set is defined by binomial coefficients, and if you look how they grow, it's like an insane growth in the number of combinations that you can make. So maybe just trying everything is not the best solution. So there's this quote by Albert Einstein that imagination is more important than experience, which probably also works here. And I guess it's imagination plus some fundamental knowledge. So it's impossible to know how every single combination of software works together, but there are some basic things that you can use for guidance, and some imagination and some problem solving skills, probably math skills, that will help you on the next steps. So when you go into school, like you study computer science in the university, which I never did, but I guess that's what they study, computational complexity. So discrete math, how to analyze how long the execution time of a program will be. People often think that this is pure theory and you will never need it in work because all the cool things are already implemented in libraries. And like maybe a few months after you graduate from university, you forget everything. Because like once you go to your employer, he tells you, forget everything you've learned in school, the world is different. But I don't think so. I think that like there's still a lot of relevance in what you study, especially if it's something fundamental. And probably one of the most important things is actually computational complexity theory, because before you run the program, you can actually estimate how much time it will take to run this program. Does it even make sense to design a solution like this? So this is some quiz time again. Let's see how your imagination works and how many of you remember the high school program or the university program. So let's imagine that we have a big string of we have a long text of n symbols, and we have a small pattern, a substring of m symbols. Let's say we want to find a sentence code Republic in all of internet, and the length of internet is n, and code Republic is m. How many operations do you think it will take to find all inclusions of m in n? Any guesses? Why not? Try. So on is the answer. That makes sense. So essentially you have a big string and you have a small string. You try every single offset of the big string to do the comparison. But when you do the comparison, it's not O1. It's actually... Oh yeah, but we study like the field of asymptotic complexity doesn't study the best case; it studies the worst case. So like ON, but this is ON comparisons, and every comparison is not a constant thing. It's not a one operation. Yes. So the obvious naive solution is O of M of N. So essentially, for every single offset of a bigger string, you try to match if it matches the query. In fact, the right answer is here, yes. So it's the naive solution is OM by N. But there's like a best case algorithm, like which works faster. And it's OM plus ON. It may work much faster, but then if you have any experience programming, you know that the algorithm that has higher or better asymptotic complexity, lower complexity or better complexity doesn't often mean that it will run faster, because besides this math part, there's also a constant multiplication factor that you should account for when you do any real performance analysis. So even though this formula is better than this formula, the vice versa. This one, the naive solution, is worse than the best solution. The result on practice may be different. So there are ways to implement the naive solution so that it works faster than the best solution, the best algorithm. Now let's, let's make, let's assume you haven't seen what's there, and let's assume you have two matrices, n by n, and you want to multiply the two matrices one by another. How many operations will it take to multiply two matrices of size n squared, essentially? So n to the power 4 was your guess. Do you remember how the matrix multiplication works? we'll multiply every row by every column to get every cell of the output matrix. So any more guesses? We had n to the power 4. Anything better? Okay. It's actually n to the power 3. In the naive solution, in the most obvious solution that you can program, it's n to the power 3. But then in the past decades, because matrix multiplications were like so relevant in computation, we've got to a point when we have n to the power 2.27, which is like a very important result for AI, because most of AI is matrix multiplications. Now let's assume, oh, I don't know how many of you have already studied graph theory. No? Not yet? Okay, so once you study the graph theory, you will realize that there are lots of problems on graphs, and graphs are some of the most challenging domains to study computational complexity. If you have a graph and you want to find the shortest distance within this graph, and a graph can be anything such as a transportation network of the city, a social graph of Facebook where all of the people are connected with edges if they're friends, and you want to find the shortest distance between, let's say, you and Barack Obama. How many people connect you? How many handshakes are there? Or you want to find the shortest path from city center to Code Republic. All of this is like special cases of the shortest path problem on graphs. And the classical algorithm that's used for this specific problem is called Dijkstra's algorithm. And the computational complexity of the Dijkstra's algorithm is on the left side. But if you know some interesting data structures, you can actually update and modify the original algorithm of Dijkstra, which uses a priority queue, to replace it with a Fibonacci heap. And if you replace it with a Fibonacci heap, one of those complicated data structures that are not in the STL, not an STD map, not an STD unordered map, not an STD priority queue, but something much more ingenious, something much more interesting, you can actually reduce this runtime complexity to this runtime complexity. And depending on the size of your graph, this can actually cut your computation time from months to days, or from days to minutes, or again, from minutes to seconds or milliseconds. This is a huge difference. The next problem is the maximum flow problem. Imagine you have like a network of pipes in the city. And this network of pipes actually pushes the water from a water reservoir somewhere outside of the city to every single household in the country or every single household in the city. You want to measure how much water you can supply to all the households every second. What is the maximum flow through this network of pipes? And this is precisely the max flow problem on graphs, or how many people can simultaneously drive in the city to get from one part of the city to another. To solve this problem with a more or less classical algorithm of Edmund Karp, you have to have like V by E steps of computation. And if you do something more complicated, you actually divide it by E. So if you have a dense graph, E is equal to V squared. So essentially here you have V to the power 5 and V to the power 3 here. And it's, again, a big difference. It's a difference between 100 operations and 10,000 operations. And the last one is my favorite. It's actually the graph isomorphism problem. And this is a big family of problems. A good example of what kind of problem this is, imagine you have two molecules. And a molecule is essentially a network of atoms connected to each other. And you want to compare if the structure of one molecule is identical to the other. So you want to do drug design. You want to see if one pattern of a network, like one pattern of a molecule matches the other one. And if you find that it matches a specific pattern, this means that you can design, let's say, a drug that targets the specific virus, such as COVID-19. So you take a network of COVID-19, you take a network that can match this COVID-19, and you see if this second network can actually come and insulate the second virus molecule. So this problem is NP hard. NP hard means it has a non-polynomial complexity runtime. So the formula that describes of how many steps it will take to actually compare if two structures are identical to each other is not even described by those power equations. It's described by more exponential equations or something even worse. So if I just draw an exponent that grows like this, I guess we all know how exponent looks like this. And then there is a graph that grows even faster than exponent, which is the factorial. A factorial of n is every number before n multiplied on one another. So like 6 factorial is 1 multiplied by 2, by 3, by 4, by 5, and by 6. And to actually compare if two graphs are completely identical, you have to permute every single node with each other and compare the two matrices with each other to see if they're identical. The number of permutations is the v factorial, and the number of comparisons is the v squared. And today, we don't even know what is the best theoretical limit of computation. So about 3-4 years ago, a professor from Chicago, Laszlo Babai, pioneered a new algorithm. And 3 years later, like 4 years later, we still don't know if his algorithm works or not. So those problems are so complicated, so challenging, that not only finding a good solution to them is hard, but after you find the solution, even analyzing how hard or how good is this solution takes years of some of the most advanced specialists on the planet. And I work on like graph isomorphism problem, and the subgraph isomorphism problem is even harder than this one. But I guess we'll get to it some other day, maybe like on a longer lecture. So probably like after this long lecture, you are completely bored because like you've learned a ton of complex stuff and you don't even know if you will ever need it. But all of this was more like a demo of what can be learned and where's like the limit of how far you can go like optimizing stuff. The reason I do all of this is I want to be able to compute and analyze more data than hopefully anyone else on the planet. But this is more like a dream case. Like you want to converge to a point when your models work faster than anyone else, when you can predict cancer better than anyone else, when you can extract knowledge better than anyone else. To do all of this on this scale, you have to learn so many different things, and the path is extremely long. I guess for me, it was like maybe 15 years, and out of those 15 years, it was like 5 years of very, very deliberate work every single day of those 5 years. Now, how to do the same thing faster? Well, there are some resources that will probably help you. Obviously, Code Republic is a very good starting step. You will learn all the basics, I guess, and after that, you will go find your job, do some work, but very often when you work in a company is limited to something, you are just responsible for some tiny thing, tiny part of the application, and you are not really learning something outside of your scope. So you can spend 20 years in the company working on something but not really progressing, not really learning new skills every single day, not really challenging your brain with some new information, new methodologies, new problems. And whenever you feel that you're stuck, the internet will help you kind of see the bigger picture. So my favorite resource of all is Arxiv, or Archive for short, which is the online library of Cornell University, which provides you with an almost endless list of scientific papers on all kinds of different topics, from physics and biology to computational complexity and computer science. So whenever you have an idea of an algorithm in your brain, you can actually check if some other people have thought about this before. You can search for similar approaches, and maybe you are not the first to come up with this solution. And in my practice, I've had so many times when I find new algorithm or design new data structure, and then I realize I'm just replicating the work of a computer scientist from some other European university, or let's say American university from 1990. A person who has designed this algorithm like years before I was even born. And then, if you want something more applied than pure theory, you can go to YouTube, and it's perfect because you can find the lectures from all kinds of professionals from all over the planet. And probably the best channel to actually use is CPPCon, which is like the channel of the biggest co-named, identically named conference in the C++ community. And it goes, like they publish cool videos every year. And besides CPPCon, there's like CPP on C, CPP Russia, and a lot of different other regional conferences. Then, if you are capable of self-learning, I would suggest just doing code reviews. just open up the big libraries that you can find in the following repositories. The Facebook and Google have a ton of different repositories under different usernames. So it will take a little bit of crawling to find the best ones. But you just look into the issues that come up in the library design. And those libraries that they develop, such as PyTorch, they're huge. There are millions of lines of code. It's unfeasible to expect that every single one of you will design your own library that is so big and so popular. But you can at least look into the caveats that they are facing once they reach this level. And maybe you can avoid those problems from the day one. Maybe you can learn from their mistakes instead of your own mistakes. And then the last one, but probably not the least, is the GitHub repository of my company. And there's this repository called CPP template, which is like just a template of a project for C++ development. And C++ is a notoriously difficult language. The documentation for C++ 20 is over 2,000 pages. And for a comparison, you can write a Lisp interpreter. A Lisp is another programming language, which fits onto a business card. Compare 2,000 pages of huge documentation and the business card. Obviously, C++ is complicated. We can learn a lot of things from other languages. But it's not only complicated as a language, the tooling for C++ development is also extremely fragmented, and you don't even know how to start programming from day one. So this repository contains like a template of repository. You can just press this button, use this template, and it will clone, or like not even clone, it will duplicate the content of this repository to whatever you need. It will contain a bunch of stuff to get you going. First of all, it has, let's say, Clang format. A Clang format is a formatting tool that will automatically manage the indentation, the styling of your code, how to actually like name the variables, I don't know, separate the string into multiple lines and stuff like that, so that your code looks cleaner and nicer. Then there's CMake lists. How many of you are familiar with what is CMake? Anyone raises hands? No? Okay. Huh? Right. So whenever you compile or interpret other language, generally it comes with the standard compiler. You just press one button and your entire project is ready for use. In C++, it's much, much worse. So people started designing many different fragmented compilers, but besides compilers, there's also build tools. A build tool is actually something relatively cross-platform, where you specify which files make up every single library of your project, every single executable file of your project. And the expectation is that once you run the CMake file, it will generate a schema for a compiler how to compile your project. I guess a couple of weeks later, once you get into those topics, Vartan will probably mention what is CMake. And this CMake file actually contains a very detailed description and basic implementation of what's needed to actually compile your project. Then there is a thing called Conan file. So if you've tried programming in Python you just do pip install and then import the library that you want. If you've used JavaScript, there is like the NPM package management tool, which is the biggest package management repository on the planet. They have over 5 million repositories, I guess. They are notoriously huge. Like there was this big story when the person created a library for left padding strings, and then he removed it from the internet, and then the internet like crashed for 2 days, just because one tiny library of 10 lines of code was actually removed from the NPM. In C++, there is no standardized package management tool, and if you just want to use somebody else's work, if you want to attach somebody else's work as a library to your code and not re-implement everything from scratch, you need a dependency management tool. And there are a bunch of those. There's a VC package, which is a Visual Studio's tool for package management. There is something called Bazel from Facebook. And there is something that I use, which is called Conan, which is becoming industry standard these days. It contains about 1,000 of libraries, pre-compiled, available on the internet, and you use this conanfile.py to actually just specify the dependencies of your project, and they will be all pulled, and thanks to CMake, compiled all together, connected to your source codes, the source codes of the libraries that you use, all assembled as one single piece. So whenever you start programming in C++ on the bigger scale, you can just use this library. It will come with this template. It will come with some standard libraries that we like to use. But if you've finished this entire process, or if you're just extremely curious about continuously doing research, about designing new algorithms, designing the best implementations for them, researching, competing, doing science every day, not just programming, not just coding, I'm inviting you to participate in my project. So it's not open source, but we'll happily hire anyone who's competent. So at Unum, we want to create the full integrated vertical solution for AI and work towards AGI over the course of next 30 years. So I've been working on this project for 5 years already, since 2015. And I plan to work for another 25, 30 years, as long as it takes. But before I get to the point of AGI, there are a ton of other topics that you can research, topics for which you can build amazing tools that other people can use besides you. So that's what we are doing right now. On our path from left to right, we are doing data storage solutions and databases such as Postgres and MongoDB and stuff like that, but we are kind of trying to do something more performance-oriented, maybe an order of magnitude or 2 orders of magnitude faster than the other solutions. Then once we finish with this, we'll probably design something like PyTorch or TensorFlow that is more narrow focused, so not as generic as those libraries, more for our purposes, and natural language processing. And finally, we are working on things such as anomaly detection, recommender engines. So those are different aspects of AI. So for example, anomaly detection is you having a list of transactions from a bank, and you need to detect fraud. So whenever you see some suspicious transactions, maybe someone sending money to Afghanistan or something like that, you need to mark this transaction so that the employees of the bank can then validate it and maybe block it so that the money is not going to terrorists. Or you want to do recommender engines. So a recommender engine is something that's used, let's say, in Google or in Netflix. So let's say you are watching Netflix movies or series. And I know what kind of movies you've watched in the past, and I know what kind of movies your friends have watched in the past. How do I design a recommender engine that is very relevant and shows you the best movie that you're most likely to watch right now? This is also a machine learning problem that requires many layers of infrastructure to be built to actually perform on the scale that I want it to perform. And the last but not the least is, let's say, forecasting. So let's say you watch the stock prices and they change a lot, or you watch the Bitcoin prices that are going up very rapidly these days, and you want to see if it's possible to design a machine learning system to forecast the price of the Bitcoin tomorrow. How do you do it? You probably design some form of recurrent neural network, or maybe a specific case of this like LSTM or transformer. All of this is machine learning, but machine learning is not just this separate keyword that exists somewhere. Even though machine learning researchers use Python libraries, those Python libraries are just wrappers for the C++ code and CUDA code that runs underneath. So essentially, anyways, you are just communicating to the same hardware. And if you know the stack the way I'm describing it right now, maybe you can find ways along this stack to actually optimize something and process maybe not a terabyte of data, but 10 terabytes of data, or a petabyte of data. And if you can process a petabyte of data, the chances are your AI model works just a tiny bit better than somebody else's. But this tiny bit accuracy improvement can be a difference between being the number one in the world and number two. And if you have a model that does, let's say, Bitcoin prices forecasting, and you are, let's say, just 2% more accurate in your predictions than your competitors, this means you can make hundreds of millions of dollars or billions of dollars in a year just thanks to you being able to optimize more layers of this infrastructure. So I've kind of shamelessly introduced my company here, but just like a final point is that if you are interested in what we do and what kind of tools we use, even if you are not really interested in going so deep into like some optimizations, you just want to see what libraries we consider good or bad, here's more or less the technology stack that we can kind of recommend, or the libraries that we find interesting or usable. We're not really using many of those libraries, to be honest. We kind of re-implemented everything from scratch as part of our own C++ solution. And we are very, very focused on clean code and compact code. So maybe sometimes we have lower performance than competitors, but maybe we have like 10 times less code or 100 times less code. So our entire code base is like 200,000 lines of code. And half of those projects here, each is maybe bigger than 1 million. And they are mostly focused like on one specific niche thing. And we kind of have a very different approach. Regardless of the libraries, there are different cool data structures, languages that we use, and everything is kind of described in detail on our website, unum.am. If you're curious, like there's a list, there's a description, there's a bunch of tables, performance comparisons between us and competitors. So just drop me a line, and I will be happy to discuss how we can work together. That's it. If you have any questions regarding the slides or whatever, I can answer before I close the laptop. Or you can just ask them afterwards. Yeah. Չէ, մերը ոչ ռելացիոն է, ու շատ է տարբերվում իր ձևով. So on our website, we have a section where we compare one of our first product, which is a database. And the question is if our database is relational or not relational. It's definitely not relational, and it's also not really SQL or any QL. So there are so many bottlenecks that we couldn't really introduce into our software. So for example, when you send a query to a database, you generally encode it with some form of language. Normally it's SQL, structured query language, or GraphQL, or something else. In our case, the performance is so big and like the latency is so low that even adding a layer of parsing your queries from natural text or from this text into like an executable action plan introduces a huge performance penalty for our current levels of performance. Okay, guys, I guess that's it. If you have any questions, feel free to just pull me from anywhere or just text me on the social networks. I'm always available, and our office is at ISTC, which is like at Yerevan State University. So you can visit us any day, and I will show you around.